Today, you're going to discover how Wagners Composite Fibre Technologies and Kehoe Myers designed and certified what will be Australia's longest fibre reinforced polymer truss bridge. Good morning and welcome to our webinar case study on Eprapah Bridge for Redland City Council in Queensland. I'm Kelly Stewart, Marketing Manager at Wagners CFT, and I'm here with Wagners Technical Lead, Dr. Ali Mohammed, and our fellow Toowoombarite and friend, Kehoe Myers Director, Bjorn Jachmann. Ali is a structural engineer specialising in civil composites with a strong technical background in FRP products at the material level, individual components and full-scale structures. Ali is manager of the design of Wagners CFT projects globally and believes FRP is the material of the present and the future. Meanwhile, Bjorn is director with Kehoe Myers, bringing more than 30 years of experience in structural and civil engineering on a global scale to the business. Bjorn's specialisation lies in the design and management of a wide spectrum of structures, including bridges, where he employs cutting-edge technology using concrete, steel and FRP. In particular, Bjorn is focused on the dynamic behaviour of bridges under pedestrian loading and the development of new connections. Welcome, Ali and Bjorn. Before we get started, just a few webinar protocols. We are recording today's event and we'll make the recording public via the Wagners CFT YouTube channel. We're going to run through Ali and then Bjorn's presentations first and hold answering questions until the end. However, you can ask a question anytime you like during the webinar via the chat tab, which you will see at the top of the screen, indicated by a speech bubble. Any questions asked will be compiled for discussion during the Q&A session following Ali and Bjorn's presentation. So, let's dive in. I would like to introduce Wagners CFT Technical Lead, Dr. Ali Mohammed.
Thank you, Kelly. Let me share my screen. Yep. Thank you everyone for attending today's webinar. Before getting into the design of FRP, I would like to touch base on the FRP applications. So basically, if you think about FRP, fiber reinforced polymer sections, They are structural members. They can be used in many or various structural applications with pros and cons for every applications, considering the environment and also considering the inherent properties of FRB. So basically, like the company started by making FRB sections 100 by 100, 125 by 125 SHS sections as electrical cross arms, but the exact same sections basically being built at longer length to make boardwalks and bridges. So the same section can be used as a driven pile, as a bearer joist, and the handrail system. And the same thing can be applied for the other applications, considering light poles and utility poles. But basically what I'm trying to say here, they are structural members. They can be used in various structural applications. When it comes to the design of FRB structures, or before we get into the design of FRB structures, talking about the design in general, there are two main components for the design: the analysis part and the design part. When it comes to the analysis part, the design inputs are being taken from the local standards, talking about in Australia here, taking the loads and design criteria from AS 1170, AS 2156, AS 5100. Talking in the US, the design inputs are being taken from the local codes like AASHTO and what have you, and the same thing in Europe. These are the analysis inputs. The analysis procedure itself is basically can be done using the well-established engineering theories and first principles, like beam Bernoulli equation theory, or like Euler buckling formula, and with manual calcs and or the in-house developed spreadsheets, or even basically like using the structural analysis software, like for example space gas. So all the analysis part is basically what we do for every other design. The design component of FRB structures is the challenging bit of the design, mainly because there are no Australian standards. However, like Engineers Australia basically refer to basically or allow us to refer to international standards if there are no local standards. So the international standards mainly are basically the Eurocode and the ASCE LRFD. So all of these component, all of these basically design codes are being developed for all the commercially available FRB. And as you know, FRB is basically very engineered material. It can vary significantly from one pultruder to another and from one manufacturer to another. So basically, you'll get like a wide range of basically like of mechanical properties or of design aspects. So what has been done basically here in Australia is basically we have developed the design guide that is specifically that cover basically the design aspects and the mechanical properties and the structural capacities of the locally manufactured FRB. This design guide is basically being developed considering international codes, the Eurocomp and the ASCE, and also at the same time considering or referring the Austro technical specification, which is the first national guideline or specifications being developed basically here in Australia by Austro. It's been published October last year. It's mainly referring to the British FRB standards, but it's a good step in the right direction considering the Australian market. So the design guide basically like make the design process straightforward. So basically we'll get the results from the analysis phase, and basically we will do it. It will be like a matter of a cross check between the member capacities and the connection capacities that are presented in the appendices of the design guide. And talking about the design guide, I would like to take the opportunity of basically of making the announcement of the design guide version 2. It's just been available to public this week, so it can be downloaded like from the company website. So the capacities and the values being reported in the design guide. As I mentioned, the design guide is being developed in accordance with the international FRB codes and with the Austro specification. And all the actual capacities and experimental capacities are being taken from extensive testing program. So like at the co-bonds level, as we can see here, like compression, the tensile, in the exact photo here, we have in a plane shear co-bond test. And also at the same time, we have like the structural testing of the full members, or individual testing of actual components, bolt connection, and all of these tests have been combined together, and we do a test on a whole system, as we can see here, a fully assembled truss being tested, and all of these values being correlated with each other, and to develop the capacity tables that we have in the design guide. So basically, we have the capacities in the design guide that can be cross-checked with the results that we get from the analysis. So basically, your M star can be cross-checked basically like with a phi mu, and considering the design reduction factors, and that would be your tick for the design. Talking about the design reduction factors, so all the tables presented in the design guide are already include the capacity reduction factor. There are three main types of reduction factors. So basically, the capacity reduction factor, the time effect factor, and the end user or the environmental factor. So the capacity reduction factor, if the capacity is being calculated in the theoretically, there are specific factors for every property, whether it's in compression, whether it's in tension, whether it's local failure, whether it's a stability failure. So this value can vary from 0.65 up to 0.9. However, if the capacity coming from an experimental test, this capacity reduction factor are calculated using a statistical analysis method, based on the number of samples being tested and based on the coefficient of variation, which is usually less than 5% when it comes to the locally manufactured FRP here, mainly because of the full automated and the high like our stringent QA system. So basically, we maintain a coefficient of variation of less than 5%. The time reduction factor, basically, it is similar to what's been applied like for timber design, and it's mainly considering that type of load, whether it's like the sustained load during the whole design life of a structure, or whether it's like the self weight and the dead weight of the structure, or transient load. And for all of these loading condition, there is a specific value. For example, 0.8 for transient load, 0.4 for sustained load, and all of these factors being taken from the international FRB codes. The final reduction factor and is the end user adjustment factor to account for moisture, temperature, and chemical environment. So this moisture condition factor, basically, or environmental reduction factor in general, it's mainly consider the type of the environment and mainly the type of material and the manufacturing method being used to manufacture that FRP itself. So it varies for strength and modulus, and vary for the type of resin, whether it's vinyl ester, epoxy, polyester, and also vary with respect to the manufacturing method, whether it's filament wind, whether it's pultrusion, whether it's hand layer. So all of these codes being taken, or all of these factors being taken directly from the code. The thing that I want to highlight here, these reduction factors are, or mainly the environmental reduction factor, is being applied at the discretion of the design or certifying engineer, mainly because these factors are being taken from the international codes that being developed for all the commercially available FRB. And as I mentioned, FRB can vary significantly from one pultruder to another. So dealing with various certifying engineers around the country and even around the globe, I know like some of them take these reduction factors as per what's presented here. Some of them consider it as 0.9, and others consider it even as 1.0. In other words, no reduction factors. Mainly because that's mainly because of the durability studies and the case studies that we have done in the past. So basically, we have done an extensive durability studies where basically samples been conditioned at extensive UV and moisture cycle with a specific temperature range, following specific ASTM standard, and all of these compounds being assessed before and after the conditioning. Another good example of that is the Cameron's Rock case study, where this structure being installed 10, 12 years ago. And after it's been 12 years in service, let's say, and going through like major floods, the floor bracing of this specific structure being replaced in collaboration like with the Brisbane City Council. Like we took that sample and we replaced it with the fresh sample, and mainly to undertake an R&D basically evaluation on a sample that's been in service for 12 years. So we took that sample back, and basically we did experimental testing on that specific sample, and basically the compound test results being tested, and it still can pass the QA pass mark that we have in system that we assess the freshly manufactured FRB against, and these QA pass mark are still higher than the actual design values that we use in the design guide. So for example, like the interlaminar shear 50, the compressive strength is 500. The sample being tested still can meet this requirement, even though the design values and the design capacities for the interlaminar shear is 44. For the compressive strength is 485 MPa. So basically, like that would give the confidence for the certifying engineer basically to reconsider how to apply the environmentally reduction factors. The final thing that I want to highlight in my presentation before handing over to Bjorn is the performance of the material, or basically the behavior of the material. As structural engineers, like we need to understand the behavior of the material to give us the confidence, basically, like to and the good understanding of how the material is going to behave in actual service. So the graph here shows the difference between the glass fiber reinforced polymer material and the steel section or steel material. Everyone love steel because it's when it comes to the structural design aspect, because it is a ductile material. It gives us enough warning before failure, and compared to the FRB, which behaves linearly elastic till failure. That sounds like a scary for structural engineers. With that being said, two key points, or two key items we need to keep in our mind here. So for the GFRB, when it comes to the design of GFRB structures, considering the high strength to stiffness ratio, the design is generally governed by the serviceability limit. In other words, the strength utilization of the material is around like 30% of the actual or of the ultimate strength of the material. The other and the more interesting part of the FRBs, or mainly the FRB that locally manufactured here, even though like it failed in a brittle manner, however, that doesn't mean the member gonna snap into two pieces, making catastrophic failure due to basically the one fiber that reinforced the member. The two members or the two sections still can remain intact after the final failure of the FRB. So a good example of that is basically this post. Basically, this post is being cast in the wrong spot, and the contractor thought rather than digging the post out, they will just knock it down with excavator. So let's see what happens here. Yeah, so even though basically this structural member failed due to exceeding its moment capacity at the ground line, and it exhibit basically a linear, or it exhibit a brittle failure by significant drop here. The continuity of the fibers kept the member as one piece, and it still can carry the sales weight of the member itself and some additional weights on the member. So here I conclude my presentation, and I will hand over to Bjorn, and I'm happy to answer any questions at the end of this webinar. Bjorn, all yours. I'll stop sharing my screen.
Yeah, thank you, Ali. That's a great presentation. Yeah, I actually will talk today about the Eprapah bridge, which was already introduced in the little introduction video. And I will focus pretty much on the member and connection design, and then the second part is more the dynamic behavior of the bridge structures, which is becoming quite important for composite fiber. So as you probably saw in the last graph from Ali, you can see that the stiffness of composite fiber is much less. So we're looking at 36,000 MPa compared to steel is 200,000. So stiffness is a problem. Strength, we are fantastic with composite fiber. But yeah, the lesser the stiffness, the easier a structure can vibrate. But talking about the Eprapah bridge first, it's yeah, the longest bridge in Australia in composite fiber, pedestrian bridge. It's 4.7 meters wide, 2.5 meter wide traffic widths, and it does have a single span of around, let's say, 36 meters. So design criteria for the bridge was at the time 5 kPa. With the 2.5 kilonewton concentrated load. Of course, we have to consider wind loads, and we have to consider flood loadings with velocity of 2 meters a second, which is preloading, and possibly some log impact. This is something you need to assess for each of the bridge design. At the time, there was actually discussion to lift the bridge far out of the water, so they tried to do it anyways, and they got some clearance of 300 millimeter in, but they still have to consider the preloading on this bridge. You can see in the cross section, composite fiber, it's quite.
Sorry,
yeah,
Bjorn.
Yeah.
Can I just jump in there? Do you need me? Would you like me to share your presentation? Because I don't think we can see your presentation at the moment.
Oh, wait a second. Then I probably got that wrong. How do I do this?
Yeah, just at the top it says share, but I've got yours here if you'd like me to share it for you.
Yeah, I think I got that sorted out now. Do we get that now, is it?
Yes, we do.
Yeah.
Thank you very much. Brilliant. Thank you.
So I jumped straight away to this first slide. So I talked about the dimension of the bridge. You can see the cross section of the bridge, and you see top and bottom chord consisting out of multiple members. Predominantly, for the deflection and the dynamic behavior of the bridge. Strengths, we don't have a problem with truss bridges, composite fiber. So this is elevation and the layout plan of the bridge. You can see on the layout there's some horizontal members which are required for the flood loading, debris loading, and it will help us as well to control the side sway of the bridge when people walking over it, and we talk about that later on. You can see on the elevation there is actually a dotted line shown at the bottom that shows you the elevation of the flood. And there's a 300 millimeter clearance to the underside of the bridge. However, the clearance is not enough. You will get some debris loading. So debris can catch the bottom chord of the bridge, and it will actually cause some significant horizontal loading on that bridge. Yeah. So, and typically when you designing these bridges, you're using programs, and Ali mentioned that before, you're using programs like Space Gas, and you can see in the model of Space Gas, and I'll probably put two snapshots in there, it's pretty much reflecting the same cross sections, and program considering quite good the E-modular of composite fiber. For truss bridges, I have to say, if it's a beam structure, you have to be careful because of the deflection. What this program doesn't consider is deflection coming out of shear. And it doesn't matter for composite fiber because it's probably increasing the deflection roughly, let's say, by 5%, which doesn't sound a lot, but it makes the material a bit softer. You should be always aware of this little property which we need to consider. When we do the design, that's no secret, you're looking at your ultimate forces, and you can see on this little graph, you know, the compressing force at the top chord is 941 kilonewton. The ultimate tensile force at the bottom chord, it's nearly the same. It should be the same. There's always a little bit of a variance in it. And you've got even some tensile forces on the top chord and some compression force on the bottom chord. The design is done pretty much using the design guide. We use the old design guide, but since today we can actually use the new design guide, but nothing really is different. But there's some complication for this one because you need to look at this truss bridge and you have to look at global buckling of the top chord. And when you look at global buckling, this is not captured in the design guide. You need to calculate your own capacities of this top chord. And you see the top chord consists out of two rows of members, altogether 625 by 6.4 SHS members. Combined, they've got this cross-section I worked out and got its I values worked out. And you have to look at the buckling length of the top chord. There's different methods around it, but one method is simply using the program. And we use space gas. And space gas actually gave you a buckling length of 5,920 millimeter, considering the stiffness of the verticals, the stiffness of some propping. I can go back where I said propping here on the side here, these members here. So you don't get a sudden failure of the bridge when it's fully loaded. And there's actually two areas you need to check. It's actually serviceability of this one. And you can see, just using formulas which are well known, you can actually got the minimum serviceability load of 1,500 kilonewton. And when you look at the ultimate design code, I only touched base on this one. You got a few reduction factors in that as well. It's actually lambda. It's actually looking at the time when the load is applied to. Then you look at the C factor, which is about talking about the environment. So what things you need to consider in that design. And you worked out that we actually got a capacity of 1,428 kilonewton compared with the buckling load of 941. So we got a lot of, let's say, redundancy in terms of strengths. So you do the same thing pretty much with all these members. And I want to show you how you're designing pretty much the connection of the diagonals in that in the truss bridge. And you see the diagonals, especially at the end, so the highest loaded one, that's not surprisingly. They got 6 bolts, 6 M24 bolts in that connection. And because it's a double shear, and you jump into the design guide, which is now the old one, you got for the M24, actually double shear, you get for one bolt 64 kilonewton, you got 6 of them, you got like 384 kilonewton capacity. This insert is non-glued, so you got the overall capacity of 384 kilonewton. The design load was 368 kilonewton. So we are pretty much fine with this connection. I can probably say we need 6 bolts in there. The member itself, the diagonal member, is a 250 by 125. Would be probably arrived with just a single member, but because of the limitation coming from the connection, you're ending up with 2 members at this connection here. Because of the length of the bridge, which is around 36 meters, and the access, there were splice joints required because the roads was pretty narrow road, so you had to really break up the span of the bridge in 3 elements, so they're pretty much equally spaced. And I marked the joints here where they are. So 36 meters divided by 3, they're probably 12 meters long each. And we actually worked with the splice joint using rivets. They're very effective using rivets, and you can see there's a lot of them in, which is a lot of work for the guys on site, but the strength of this connection is, I would say, even much, much better, I would say, than the bolted connections. One thing to consider is the rivet connection, especially top cord. There's a lot of axial load in it, compression. There might be a failure of buckling possible of this connection plates. The connection plates are 5 millimeter thick, each side. We got, again, Wagners did a lot of tests, so we know what the capacity of the plates are. Again, I tell you, there's a heap of capacity in that connection. That's the last thing what will fail in that design. So it was very quick, a little bit of a design of this bridge structure. And I want to move on now to the dynamic behavior of bridge structures. And I want to start with a little video I want to share with you. It's actually the Tacoma Bridge, which was constructed in 1940 in the US. It was crossing this bay, and during the construction, they already noticed that there's a lot of sway going on the bridge structure. And on a particular day in 1940, there was consistent wind around 60 to 65 kilometers an hour, and the bridge started to sway. And it's, you can see in that video how significant this sway was, and that was never experienced before in that world. You would see the local newspapers came to site. One guy parked his car on the bridge, which is quite extraordinary. He just walked away, you know, it was nothing. But you can see what's happened later on. The bridge actually collapsed just under a wind load of 60 to 65 kilometers per hour. So nobody ever thought about that would be possible. And there's other means of sway for bridges. And I want to bring up the Millennium Bridge in London. It was opened in 2000 to the public, and you can see on that video straight away people walking over the bridge, and it was swaying sideways. Never watched before on a bridge structure. It was a very slender structure anyways, and actually designed by Sir Norman Foster. And all the engineers, the architect, were very surprised what's going on there. So it was quickly was named the Wobbly Bridge by the locals, and they had to shut down the bridge 2 days later, so it was too severe. They shut down the bridge to the public, and they said, we need to improve it. What they actually done, they actually talked to a few smart engineers. One of them was actually based in Germany. I know this guy, this Professor Peterson. And they designed some shock absorbers they later installed in that bridge. But the whole rectification work took them 2 years to get that under control. And they got it under control since they installed the shock absorbers. And I think there was more than 60 of them along the bridge structure. It stopped swaying, so people walk over it and they don't get this pretty uncomfortable feeling of walking off the bridge. You see now that's after they actually rectified the problem, people walking off the bridge, and it stopped swaying. So, but we don't want that happen to our bridge. So that's why we want to dive in a little bit into the dynamic behavior of bridge structures. First, we have to understand what does it mean when people walking over the bridge. So this is roughly how the characteristic looks like if a pedestrian walking over the bridge, and that's the sort of vertical forces they inducing into the bridge structure. So this is for a person with a body weight around 71 kgs. So you can extrapolate it if it's 80 kgs, all the numbers are going up. So people typically walking with a frequency between 1.5 and 3.5 hertz. That's actually depends how tall you are. It depends a little bit which country in. Smaller people walking with a higher frequency than taller people, so that's a little bit different. But because they're smaller, the forces inducing into the structure is actually a little bit less. And you can see on this graph here, this, for example, might be the left foot, if you could see my cursor, and this is the right foot, and so on. So it is a little bit a wobbly characteristic for the vertical loading. And if you, in this critical frequency, it's a 1.5 to 3.5 hertz, with your bridge structure, you have a problem. You have to look at that a little bit closer. So when we did that here for Eprapah bridge, and we used a few methods to calculate the frequency of the first bridge. So the first mode of this bridge was actually 3 hertz. So we are in that critical area. Actually, the bridge code AS5100 said if you're below 5 hertz, you should investigate further what that means for the bridge, how it behaves under pedestrian loading for vertical resonation. And the second mode was already at 8.2 hertz, so we well above the 5 hertz. If you look at the figure how the bridge will sway, you see it's an easy way to get the bridge to sway in the first mode. It's getting much harder to get the bridge to sway in the second mode because you need to get the people to work together. So you have to apply the forces on the right side of the bridge, but then you have to take away the forces on the left side of the bridge. But it's very unlikely that it will happen. But you can't rule it out, and I will show later a video that is actually possible. So to understand how a bridge behaves, you need to understand basic physics of that. So I'll put in, just throw a little bit of a formula to you. It's just the equation of the dampened bridge structure. There's a few numbers in it, you got pretty much part of the frequency. Then you got actually a value in it, how the structure is dampened. This is zeta value. And then it's pretty much the time and then the amplitude. And to understand the frequency of a structure, I put the formula in it, and it's a very simple formula, but it describes everything, and you have to understand for how the structure behaves. So you can see the square root, and you see there's the E modular, there's the I value above on the top, of this equation. And then underneath it's M, it's a mass. And then actually the length of the structure is underneath as well. So that's what it actually tells you. If you have to change something on the frequency, if you want to get it lifted out of the critical area, you can change the I value with some things potentially. But if you're increasing the mass, you're actually decreasing the frequency. So of course, if the bridge is longer, the frequency will drop. So whatever you're doing on the structure to modify, you have to understand what you're doing and what it does to the structure. Sometimes you can actually stiffen up the structure by filling some concrete into the top chord. Doing that, the I value goes up significantly, but the weight goes up as well. So you always, there's always a disadvantage as well. So you have really to look at that. And you have to see as well what's the damping ratio is of composite fiber. This is actually coming out of a test they've done, and they compared the damping ratio of the composite fiber structure compared with reinforcement structures or reinforced concrete and steel structures. As you can see, composite fiber, the damping ratio is 0.62 in the experiment, so work that out. It's actually much better than steel, but not as good as concrete. What this damping ratio actually describes, and if I jump back, it's actually the ratio how much the frequency, the swinging, will actually decrease from one swing, let's say. So now we're looking into the bridge code. So the bridge code describes, gives you some guidelines how to calculate your maximum acceleration, because that's what you're saying, oh, that might feel uncomfortable. There's a formula on the bridge code you can use, and I've used it for Eprapah bridge, and we worked out there's an acceleration. It's a maximum of 1.6 meters second squares. That's what we worked out using the bridge code's formula. The allowable acceleration, according to the code, is actually 0.59 meters per second. So we're well above that. So of course, then we have to dive a little bit deeper into this whole design and say, okay, what is it really? So there's, of course, you can dive in, and I use the formula, which is very commonly used for investigating this structure. P naught is pretty much the force accelerated, provided by the pedestrian. K is the stiffness of the structure. Beta describes the ratio of the frequency of the bridge and the pedestrian walking over it. And zeta is the damping ratio. So based on that, there would be a maximum oscillation of plus minus, let's say, 2 millimeters in the center of the bridge. It's not a lot. So velocity of this one is here just 0.04 meters a second. It's not a lot. Acceleration is based on this, is 0.67 meters per second square. So it's a little bit higher what the bridge code would recommend. But then you have to see it in conjunction with the oscillation, which is just plus minus 2 millimeters at the bridge center, which is literally nothing. So when you walk over it, you probably feel a little bit of a vibration. Probably as a person who's walking over it doesn't feel it. It's probably a second person standing on the bridge would feel it. But I don't think that's uncomfortable. But I just want to say, yeah, we definitely have to look at this behavior of the bridge. The second thing is, of course, the horizontal sway of the bridge. So if this is typically when you be a person walking with, let's say, 2.5 hertz over the bridge, 1.25 hertz result into horizontal sway. That's what's actually found out when they investigated the Millennium Bridge, because before that, they never really looked at that. It was never a problem. So the characteristic of this horizontal sway is very even, and people walking over bridges starting swaying horizontally, they're walking like, they call it the seaman walk, because you try to balance it out. And while you're balancing it out, you're actually increasing the sway because you're applying more and more forces on it. Of course, we looked at the horizontal frequency as well, which is actually 2.1 hertz, higher than 1.5 hertz. And that is recommended by the bridge code, AS5100. And the second mode is 4.4 hertz, so it's well above. Yeah, we are safe in that regard. However, I looked again, what would be the oscillation? So what would be the velocity and acceleration of that bridge horizontally, people walking over it? And it's very, very minor. You see it's plus minus 0.3 millimeter, which is literally nothing. Velocity is very, very small. Acceleration, you probably don't even feel that. It's just some horizontal sway happening on the bridge. So it sounds very theoretically about the sway, but you remember the videos I saw that showed, of the Tacoma Bridge and the Millennium Bridge. It's possible, but there's another video, just a short one I want to show you. It's actually of a bridge somewhere in the States. I don't know where it is, but this bridge is, can sway a lot and by pedestrians, and actually people do it on purpose, yeah, walking over the bridge and try to get it to sway. You can see how it sways. And you see, it's the young guys, they have a lot of fun with that. So this thing, we don't want to happen to our bridge, and I don't think our bridge in Eprapah will respond like that. But you can see how much it can sway, and that's what I call uncomfortable. You see this guy walking, jumping on the bridge, he's actually enjoying that. I'm not sure if I would enjoy that much. I would be worried about the structural integrity of the bridge, but you can see how much it can sway, and if you want to, you can actually, he gets airborne. Yeah, I want to stop that because this video goes on for a while and they're doing all sort of crazy things with the bridge. Yeah. I want to say thank you for your attending that, and yeah, I hand over to Kelly.
Thank you very much, Bjorn. We're about to go into the Q&A session of this webinar, and I see Sam Price. Thank you very much for putting your question in there. If anybody does have some questions for Bjorn or Ali, please pop them into the chat box now. Just to give Bjorn a bit of a break, I'm just going to tell you a little bit about some things that are going on at Wagners at the moment. So bear with me while I share my screen. Okay, so for the next month, electronic car drivers in Port Macquarie, New South Wales will get the chance to trial Australia's first electronic vehicle charger in a light pole. Essential Energy is conducting the trial along with EV charging company EVX and Wagners CFT as proof of concept that EV chargers can be rolled out quickly utilising existing electricity infrastructure. The light pole itself is manufactured here in Australia by Wagners CFT from Fibre Reinforced Polymer and is electrically insulating, so there's no touch potential, inert and non-leaching, so it's perfect for sensitive environments. It's durable with a 50-year design life, carbon conscious, contributing to fighting global warming through reduced embodied carbon, and it's resistant to rust, rot, corrosion, termites and acid sulphate soil. The trial itself aligns with the Australian Government's National Electric Vehicle Strategy, which aims to pave the way for better EV affordability, access to charging stations, and a massive reduction in emissions nationally. You can use the QR code on the screen if you'd like to read more about the project. If you don't have a QR code reader, I'm just quickly popping that URL in the chat there now for you so you can access it. Bjorn has done an amazing job today as our guest speaker on this webinar series. So if you'd like to have a crack at being a guest speaker on our webinar series, and you've got a great project that's really worth talking about, now's your opportunity. It's easy to apply. Just contact us here at Wagners CFT. Let us know a little bit about the project and yourself. And being a Wagners webinar guest speaker is a great way to promote your business, increase industry connections and raise your own personal profile. So again, there's a QR code on the screen there, which you can use to access that online form, or I've just put that link in the chat box there as well. At this stage, I'm going to welcome Wagners CFT General Manager Ryan Leeson to the webinar. Ryan is going to help facilitate the Q&A session with Ali and Bjorn. Ryan, let's dive in. I see there's some questions there.
Yeah, Bjorn, good morning, everybody. Bjorn, we'll jump straight into the first one from Sam Price. With FRP modelling of structures in space gas, is it good practice to use the offset tool to represent the connections more accurately, or are there better ways of modelling to get the most accurate results?
Not sure about the offset tool. Probably have to understand what that is. Offset, is it in the space as well? Oh, good question. We modeled that bridge actually as it was constructed, so there was an offset in the nodes in it as well. So it was a little bit of a moment inflicted in the top chord as well, which was pretty minor. Yeah. But yes, you can use it. Not sure if it's better, yeah, but yeah, definitely worthwhile considering that. Yeah.
Okay, thank you very much. I got one. So with the diagonals that you talked around, they were optimised around the maximum stress areas, were they? So the diagonals closer to the centre of the bridge with lower stress were a smaller member than the ones on the end?
Yes, what you pretty much do, because of the truss bridge and it got this double top chord, so you're using one type of diagonals. I think it was a 125 SHS. So you see we doubled up where we had the higher connection forces, and then of course you're going down to the 125, which fits in quite well into that gap, and that's why you probably could have done 100 SHS, but it wouldn't work in terms of constructability. Yeah.
Okay, we've got a question from Bruce here. Were there any additional design considerations required for the, more on the construction side of things, for the transport or lifting or landing of the bridge? And maybe even you could speak more broadly around that for other bridges that you've designed over the years.
It's more broadly, man, you can see, I think it wasn't shared, but there is a lifting design has been prepared from the Wagners install team, how you lift that in place. And there's always part of this whole design is the lifting design to make sure it's a safe install. You can't just simply fix it somewhere. But generally think about it, if it's a single span bridge, yeah, it can span very far, but just a matter where do you connect the lifting points to here.
Yeah, and if I can comment on the last question, that is the main reason why the bridge is being spliced. Yeah, like 35 meter, 36 meter bridge. In the past, like we have transported plus 30 meter bridges being transported as one full bridge. But here, considering the location and the restricted access to the exact location of the bridge, that's the whole reason why this specific bridge is being spliced.
Yeah, that's right, because in theory, we could install it in one piece because of the weight. The weight is very light compared with other materials, but there's other constraints like access, you name it.
Okay, thank you very much. Bjorn, do you think we've pushed the boundaries on what is possible? Do you think we can still go push them further than this, or do you think this is starting to cap out at the maximum length you'll go with the bridge?
I know we can go further. I've done some case studies on a 70-meter bridge, which hasn't become reality yet. But I reckon with some more testing, some connections, I'm confident we can go that far and even further. I mean, we've done some early work together with Ali on some cable bridges as well, which were, I can't remember, was more than 100 meters. Yeah, I can't see the limit. What you can do with steel, we can do with composite fiber, I'm pretty sure.
Very good. And last question. Here we go. Sam's just come in again. Is there a preference for riveted or bolted connections, given they both work for a specific project? Yeah, and that's a good comment, Bjorn and Ali. I think the riveted bridges, where do they sort of tap out for length, and why and where do we move across to the bolted connections?
Look, in terms of, I like the splice joints with riveted connection because the flow of forces is better through the rivets than through the bolts, personally, I think. But there will be other reasons as well of constructability. Man, think about the number of rivets you have to put in. It's not funny. But for splice joints, I wouldn't mind. But if your bridges are bigger, I think about now the 70-meter bridge, where you definitely need to splice it. We might come up with some other ideas, and yeah, we're open for everything, Ali, isn't it?
Yeah, exactly. Yeah, but if we're talking here not only about the spliced connection, if we're talking the connections of the bridge overall, yeah, that's why like there are two types of designs. So basically the riveted truss bridge and the bolted truss bridge. And the main reason we go with riveted truss bridges mainly because they are usually like shorter spans, and we have the cords and the verticals and the struts all in the same plane, and we can use like fish plates, and that's usually adequate for smaller span bridges up to 15, 16, or even 18 meters with 3 kVA loading. However, if the client requirement, because I think one of the comments was saying like QWPS insist on bolted truss bridges, even with these shorter span bridges, we still can have them bolted. They will be like over designed, and that's why we opt out basically like to use riveted truss bridges mainly for cost efficiencies and more cost effective design. But if that's the requirement on bolted truss bridges, we still can use like double cords and have the verticals and the strut sitting between the two members of the top and bottom cords and have the bolt connections if that's the client requirements.
Okay, thank you, Ali. Just conscious of time, we will have to hand back to Kelly quickly, but just for people that are familiar with using the design guide, what are the key changes between version 1, which I think is a couple of years old now, and version 2 that's about to be released? Yep. What are just a couple of the key points for people to look out for?
Yeah, the main key update is basically the new profiles and the relevant capacities, and also like more experimental test data that can be used directly in the design. Basically like more bolt connections. So basically not using the anti-crush block insert. We have introduced basically the steel push insert, which is basically a steel tube going into the member. So we have the capacities. They have slightly lower capacities, but they still can be considered as a design option. And a few bits and pieces been updated from releasing version 1. So the main things are new profiles, more experimental data.
Fantastic. Well, thank you very much, Ali, and thank you for the questions coming in. If people do have additional questions, by all means, Ali's part of the team. Shoot them through, and we'd be glad to get back to you. Ali, do we want to squeeze in that? Will someone squeeze in that last question? What was the weight ratio to that in steel? Looks like that's a question from Edward.
It's a good question, and it's a common question that we usually get. I don't have an exact weight ratio because we haven't done the design in steel yet. But usually with the FRB, since it's lighter in weight, usually like they are way lower compared to steel bridges, and that's what it seems basically like a promising to the contractors, because that make their site install much easier and much quicker using basically like lighter cranes and what have you.
Wonderful. Well, I'm conscious of time. Edward, we'll follow up those questions with a follow-up email after this webinar today. So I'm just going to quickly share my screen. That does conclude our webinar for today on Eprapah Bridge. Thank you very much, Bjorn and Ali, for your contribution and sharing your excellent knowledge. Before we do go, I'd kindly ask if you could complete the feedback form. I'm just putting the URL code for that in the chat there now, just in case you don't have a QR code reader. Look, these feedback forms are so valuable for us to help understand, what other content that we can bring you. How can we improve on these webinars? So if you could take that 2 minutes now and complete the form, I would be most grateful. I also just want to let you know about the next webinar, which is coming up on the 25th of June, where we are going to be demystifying the pedestrian design codes by looking at the top 10 most frequently asked questions of our design team and answering them. Our guest speakers will be Design Manager Jason Ziski, I always get stuck on that, and Pre-Construction Manager Stuart Baker from Wagners CFT, as well as Acting Director of Structures Evan Lowe from the Department of Transport and Main Roads. So you can use the QR code on the screen there to register for that webinar, and I will just pop the link to that in the chat there now for you as well. All of our webinars are always available on the website. If you go to wagnerscft.com.au, you'll be able to go to the webinars tab at the top of the page, and all of the webinars that we've had are there, and anything that you want to sign up for will also be there as well. So we're going to exit today on that fabulous little video that we came in on about Eprapah Bridge. Again, thanks so much for coming, and we look forward to seeing you in June. See you guys.